Okay. So just so everybody's aware, homework 4 is still being graded. I expect to get that back pretty soon. I haven't really been in a super hurry to get that one graded because that was covered on the exam. You all had the solution, so as long as you get your grade at some point, you're good. T-beams and doubly reinforced beams is due next Wednesday. You all have your exam 1 grades. They're posted on Blackboard, but I turned them off. I'll turn them visible probably here at some time today. One other thing I'll mention, I went ahead and cleaned up the YouTube playlist, so it's all in order, it's all processed and all in one location. And sort of my motivation for doing that sort of is what happened with steel design, because there's actually there's a problem with the steel design lecture last time. It didn't record, so that was sort of my motivation for doing that. But yeah, that's cleaned up to date, ready to go. Let's talk about doubly reinforced beams. Well, any questions so far? Any questions on T-beams or the exam or anything? Okay. All right. We kind of talked about this a little last time. We didn't quite get into it, but I just want to recap. So we've handled T-beams, and we're in our last bending-related topic, our last moment-related topic, which is doubly reinforced beams. So this is an instance where you have a situation like this. You have steel that you're considering not only the steel on the bottom of the beam, but steel on the top of the beam as well. And so just so everybody's aware from a notation standpoint, we're going to have primes show up. So AS prime, D prime. So just to make sure everybody's clear on that. The main complication with a doubly reinforced beam is to try and assess whether or not the steel has yielded, and by what I mean is the steel in compression. Now what I do in order to assess that is I compute the strain in the steel in compression. So this is just similar triangles. So 0.003 is to C as whatever this value is to C minus D prime. So I know you're probably used to D minus C. Instead, it's C minus D. And the reason it's C minus D is because we're looking above, not below. We're not looking at this value down here. We're looking at the values up here. And it's not D, it's D prime because we're talking about the steel in compression. So we're calculating a strain in the compression steel, hence this epsilon sub S prime. Now what we do is we compare that to the strain at yielding to see whether or not it's yielded. And if it has yielded, then the problem, to be honest, gets pretty easy because we know what the compressive force in the steel is. It's area times Fy. But if it hasn't yielded, which is very possible, if the compression steel hasn't yielded, then the force in the compression steel is not AS times Fy, it's AS times whatever that stress value is. And what is that stress value? Well, it's E times the strain. And what is the strain? Well, it's 0.003 C minus D prime over C. So if the steel hasn't yielded, what happens is this. You have the compressive force in the concrete, 0.85 FC prime AB, and let me sort of write that out. So this right here, oh, I can do better than that. So this right here is just 0.85 FC prime AB. So what we're saying is that beta 1C, this term here, that's just A, right? And because that's what A is. A is beta 1 times C. So this is the compressive force in the concrete. This is the compressive force in the steel up top, and this has to equal the tensile force in the steel below. And so if you multiply the whole thing by C to try and get rid of this fraction and do a little bit of algebra to sort of lump everything together, what you end up having is you have a pile of junk times C squared, a pile of junk times C, and a pile of junk by itself, and that has to equal 0. So you end up having a quadratic equation where you have to figure out where the neutral axis is such that C equals T. That's only the case if the beam, or if the compression steel has not yielded. If it has yielded, the problem gets real easy real quick. So it's just something to keep in mind. Let's do a couple of examples to try and illustrate what's going on here. And so this problem, I have 3 KSI concrete, I have 60 KSI steel, I have 4 number 11s in the bottom, so the area of steel is 6.25 square inches, but I have 2 number 9s up top. So I now have a new parameter, it's AS prime. and AS prime is 2 square inches. D prime is 2.5 inches, D is 24 inches, and so on and so forth. So with that, let me go ahead and just get right into it. Sorry. So it's 3 and 60, 3 and 60. Is this recording? Okay, good. I'm a little paranoid about that. That is a big beam. That's a little better. Can everybody read that? Okay. All right. Everybody with me so far? Now, we have, what we've got here is 60 KSI steel throughout. Whenever you're doing a doubly reinforced beam, one of the things that you ought to calculate before you even do any analysis on the beam is to go ahead and compute the strain at yielding. And so that's Fy over ES. So that's 60 KSI over what? There we go. That's the number I'm going to burn into the back of your memories. So that's 29,000 KSI. Don't forget that little K and that little S and that little I. Don't forget to write those letters out. Okay, and so what does this come out to be? It's small.
0.00207.
207, that's good enough. Okay, and so the reason why we want to compute that right off the bat is because whenever we're doing a reinforced concrete beam that's doubly reinforced, we have to assess whether or not the compression steel is yielded. And so we don't know that if we don't know the strain at yielding. So we might as well do that now, okay? So let's do some analysis. Now, we're going to start off, this is how we're going to do this. We're going to start off, we're going to assume that the compression steel yields. Okay, that's the easiest thing to do right off the bat, and hopefully the compression steel yields because it makes the analysis a lot easier. So we're going to start off assuming that it yields, and we're going to see whether or not that assumption is correct. Now, let's just do some fundamental analysis here. Let's go back to basics. Whenever you're analyzing a beam, the first thing that you have to do is you have to essentially determine where the neutral axis is. And you're determining that neutral axis using what principle? When we solved for A for singly reinforced beams, we solved for it, but we solved for it based on what underlying principle with the beam? What's that? Equilibrium. In other words, that the compressive force had to equal the tensile force. Now, the problem with a doubly reinforced beam is that we don't have just one compressive force, we have two. So we have the compressive force in the concrete plus the compressive force in that upper layer of compressive steel has got to equal the tensile force. Okay? Now, how do we do this analysis? Well, what is this? Somebody help me out. What's the compressive force in the concrete? That should be easy. Well, no, that's the stress, but how do you determine the force? Remember, we take 0.85 FC prime AB. Is everybody with me on that? Okay. Now, what about this? What about the compressive force in the steel? Okay. Well, what I'm doing is I'm assuming that the steel has yielded. So I know what the stress is. The stress is Fy. Okay. What about the area? Okay. Well, the area is AS prime. So it's AS prime times Fy. And that equals the area of the tensile steel times Fy. This is the only tensile force that we have is generated by this steel. So it's the area times Fy. Is everybody with me on this? I mean, I'm just writing some equations and stuff on the screen, but I want to make sure that you see where this stuff is coming from. Everybody with me? Now, what don't I know in this equation? A. I don't know A, right? So how would I solve for A? Well, I can subtract this over, right? Can I factor something out? Fy. Both of these terms have Fy, and then divide. So I propose that A is AS minus AS prime times Fy over 0.85 FC prime B. All right, so plug and chug. So this is 6.25 square inches minus 2 square inches. 60 KSI, 0.85, 3 KSI, and then 14 inches. And so what does that come out to be? Excuse me. Give me one more. 7 point. Do I have seconds on that? All right. Now tell me what C is. A over beta 1, which is 7.143 over 0.85. So tell me what that is. 8.4. It's like 8.40 something. Everybody okay with that? Now, anytime that you ever calculate this distance C, that should tell you that it's time to start calculating some strain values. So the first strain value I'm going to compute is the strain in that upper layer of steel. And so that's 0.003, and this is a new one, C minus D prime over C. 0.003, and this is 8.403 minus D prime. D prime is what? 2.5 inches. This is, sorry, oh, wrong one. 8.403. Okay, and so what does that come out to be? 0.00211. So what does that mean, Miss Aldrich? What's that? Less than what? Well, it's not less, it's more than. So does that, so our assumption, was it good or not? Exactly right. That means that when we assumed that the steel yielded, we were correct. We were correct because this strain is greater than that. All right. You collected on your debts. All right, so this is, so what we'll say is this is greater than or equal to epsilon sub y, so assumption was valid. Now, since I'm feeling, yeah, oh, yes?
So there isn't some like ACI requirement that could tell us if it's yielded or not?
That's a great question. Is there some ACI requirement that could tell us it's yielded? No. Okay? And the reason why is this. The ACI limits on strain are only limits on strain and tension. The steel in compression, it could yield or not. You know, there's no real way of figuring it out without doing it. That's a great question. So that epsilon has to be greater than or equal to 0.004 is only on the strain in the bottom. Now, since I'm feeling happy about all these strain calculations, let's do another one. Let's compute the strain in the bottom. And so that's 0.003, and this is be the one that you're most comfortable with, D minus C over C. 0.003, 24 inches minus, whoa, I don't know what happened there. The screen got all loose on me. Sorry. So that's 8.403 divided by 8.403. And what is that? Say it again, 00557?
Yeah.
Do I have a second on that? Okay. Now, that should tell you two things. The first thing that it tells you is that the strain is greater than or equal to 0.004, which is good, right? That's a limit we want to meet. But what's the second thing that it tells you? It's greater than or equal to 0.005. What does that tell you? Phi is 0.9. All right. Okay. Everybody with me? We're not done because we have to actually do the analysis of the problem. In other words, we have to actually determine the moment capacity. So let's look at the moment capacity. So let's go back and sort of assess equilibrium again. Now, what do I mean by that? Let's assess equilibrium. We have three forces on this beam. We have the compressive force in the concrete, we have the compressive force in that upper layer of steel, and we have the tensile force in the steel down below. Now let's start off with the last one. What's the tensile force in the steel down below? It's ASFY, right? Is everybody okay with that, or am I going too fast? All right. So this was this 6.25 square inches. This is 60 KSI. And what does that equal? 375. Now what are the units? Kips. Do I have a second on that? All right. Now what is the compressive force? Let's do the top one. What's the compressive force in the concrete? Say it again. There you go. 0.85 FC prime AB. So 0.85 F, so write it again, actually put the values in. What was FC prime on this one? 3 KSI. A, that was 7.143. And then B, I don't remember what B was. 14. And so what does that come out to be? Now, if you actually tracked your decimals from the previous calc of A, you should get an even number. 255. Do I have a second on that? Not an even number, just like a whole number. Now, what about the compressive force in the steel? How do we determine that? There you go. The area of that compressive steel times Fy. And so that is, what was the area up top? I don't remember. 2. What does that equal? 120. I don't need a second on that one. So just a note off to the side. We know the tensile force is 375. The compressive force is CC plus CS prime. What is that? 375, right? Remember, compression has to equal tension. Otherwise, the beam is going or is getting away from you. It is running away. All right? So compression always has to equal tension. Now, I'm lazy, so I'm going to copy this over. We'll copy this down. You all can put this on your notes, there. But remember, when we compute a moment capacity, we need two things. We need a force and what? A distance. So we need a moment arm, right? So, because remember we have, if you have a force here and a force here and some distance there, that the moment capacity is F times Z, right? So what we need is this. We need moment arms. So what I'm going to do is this. I'm going to sum my moments like I did with T-beams. I'm going to sum them at the steel. Because remember how that worked? We said we're going to sum moments at the steel. So we need the moment arm to the flange couple and the moment arm to the web couple. Remember that? So we're going to do the same thing here with doubly reinforced beams. We're going to sum moments at the tensile steel. Now remind me, what was A again? It was 7 point. Okay, so would you agree that the stress block probably kind of looks something like this, where this dimension here is A, which is 7.143? Would you agree with that? So what I'm ultimately looking for is I'm looking for a Z for this compression steel and a Z for this concrete. So let's take this. How far is it from this layer of tensile steel to the center of that block? We've already done this one before. We did this one for singly reinforced beams. D minus A over 2, right? Because from here to the top is D, then go down A over 2. So this top one, this one is D minus A over 2. Now what about the compression steel? What is that moment arm going to be? Think about how far is it from here to there? How far is it from the tensile steel to the compression steel? It's D minus D prime, right? Because from here to the top is D, go down D prime. So this is D minus D prime. So therefore, I propose that Mn is, for a doubly reinforced beam, C sub C, D minus A over 2, plus CS prime, D minus D prime. What do you think? That's not too bad, right? Did that go too fast, or does anybody have any questions? So Z sub C, okay, so here we go. Remember, we're summing our moments from this lower layer of steel down below, right? So here, let me erase this real quick. So let's say that this cross right there represents the center of the compressive force in the concrete. So I propose then that here, let me see if I can. Let me see if I can erase this a bit. So this dimension here, that's A, right? That's A. So I propose that this distance right here, that's Z sub C, from the center of the tension force to the center of that compression force. So this force right here, or this distance right here, from here to here, that's ZS prime. Because I'm summing moments here. So it's this blue force times that moment arm plus whatever in this compression steel times that moment arm. Everybody okay with that? Well, no, we summed it at the steel as well, because imagine that this compression steel was gone, right? We'd have a force times D minus A over 2, because that's what we had before, right? So no, we were always summing here, we just kept it easy. So. Everybody okay in this? I want to just throw a formula out there and you don't understand it. So.
So we're saying that compression steel yields before the tension steel?
No, I'm not saying that. I'm saying that when this beam is experiencing failure, the tension steel has to yield. The question is whether or not the compression steel yielded as well.
But does it really matter which one yields first?
No, not really. Like I said, adding compression steel can give you some benefit on some long-term performance or anything like that, but it's not like it doesn't affect whether or not it's a tension-controlled section or a compression-controlled section. It doesn't affect what phi is. The only thing it affects is our capacity. Everybody okay with this? All right. So this is what? 255 kips. This is 24 inches minus that plus 120 times that. And so what is Mn? Yeah, what'd you get?
7789.37.
Okay, first off, are we getting seconds on the count? Now, what are the units? Inch kips. So in foot kips, what is that? And remind me, what was phi again? So, oh, that's horrible. Phi Mn equals what? Everybody good? All right. If you got questions, please feel free. I get the feeling that maybe there's a couple things that's a little fuzzy. So, I mean, if you got a question, let me know. You're not going to hurt my feelings. We got plenty of time. Well, no, that's the bending strength. That's how much it can handle in bending. Well, we did, kind of. That's a good point. Let me say this. Let me go back to what we did with beams. Like, what was the capacity of a singly reinforced beam? It was ASFY D minus A over 2, right? But why did we use ASFY? What is ASFY? That was the tensile force, right? And what was the compressive force? It was 0.85 FC prime AB. Why did we use ASFY as opposed to the other? Because we were lazy. We just had to multiply two numbers together as opposed to four. So it didn't really matter which one we used because in a singly reinforced beam we know C equals T. So it didn't really matter which one we used. I was just being lazy and using the one with two variables as opposed to the one that has four. Whereas here it's a little different because there's not just a compressive force and a tensile force. There's two compressive forces. So to keep everything straight, I'll say let's just sum my moments here. So it's a compressive force times a moment arm plus a compressive force times a moment arm. I could say plus a tensile force times a moment arm. Like I could take this equation and say, plus some tensile force times some moment arm. But how far is it from the tensile force to itself if we're summing moments? It's 0. It's like when you're solving reactions in a beam, right? You sum the moments at A to determine the reactions at B. It's not that you're not considering it, it's that you're summing moments at this one particular location to eliminate that variable. It's kind of the same thing here. So, like we could have summed moments maybe in the middle, and all of our, like we would have had three, and then all of our distances would have been different. Does that make sense? I mean, Do you have a question? I mean,
So basically, move the moment wherever you want software.
well, just summing moments wherever is convenient. So, and typically in concrete design, we typically sum moments at the tensile steel. So that's just typical sign convention. So. All right. Any questions, everybody? All right. Let's let this soak in. We'll finish our second example next time, okay? I will see you all in, for the most part, in about 10 minutes.